Welcome to the video tutorial for the Unit 9 homework packet. Today we are working on pages 9 and 10, covering the ideal gas law, which is this equation, PIV-NERT. So pressure times volume equals N, the amount of gas, times the ideal gas constant, times temperature. And that's all explained on the back of your periodic table. Okay, the ideal gas law is right here. There's PIV-NERT, and it tells you what P, V, N, R, and T are. And the ideal gas constant is also listed right here. R equals 0.0821. Okay. So looking up here, we're still looking standard temperature, and that's written right here. Standard temperature is equal to 0 degrees Celsius and 273 Kelvin. Okay. Standard pressure is equal to 1 atm. Alright, when we're going from Kelvin to Celsius, Kelvin is the bigger one, Celsius is the littler one. So if we're going to Celsius, we're getting smaller, so we're going to subtract that way. So I would say 225 minus 273. And that's going to be negative 48 degrees Celsius. When I'm going from Celsius to Kelvin, I'm getting bigger. Alright, so I would say negative 40 plus 273 is 233 Kelvin. Like that. Okay. Make sure you are doing 4 and 6 on your own. Alright, again, just like when we were doing the other gas laws, we have to calculate in Kelvin. If they ever give you, like this one, they gave you a temperature in Celsius, you have to convert it to Kelvin before you can plug that into your equation, or you will get the wrong answer every time. Okay, let's move down here. Again, the most important thing we can do is going to be to box and circle our givens and our unknowns. So let's look at number 9 together. On this one, they are asking me how many moles. So I'm solving for moles, which in the ideal gas law is represented by N, would occupy a volume of, so here's a volume, liters. There's a volume. Here they give me the pressure, and here they give me a temperature, but I'm going to cross it out because I have to calculate in Kelvin. So to go from Celsius to Kelvin, I'm getting bigger. I need to add. Okay, so 100 plus 273. My temperature is 373 Kelvin. So now I've got PV, I'm looking for N, I've got T, and R isn't in the question, but it is on the back of my periodic table. So I'm going to write that down as well. That R equals 0.0821. And we can plug those into our equation. Now, you don't have to, but I kind of recommend manipulating this equation before we plug anything in for it. Okay, so if my equation is PV equals, I'm going to switch ink here, N is what I'm looking for, moles, RT. I want to get N by itself, and in order to do that, right, I have to unmultiply by RT. So I'm going to divide both sides by RT, because N times R divided by R will cancel out, N times T divided by T will cancel out. So really the equation I'm using here is N equals this, P times V over R times T. And now that I've just done it nice and easy with those letters, I can plug in some numbers. So I'm going to say N equals, my pressure is right there, 0.98 times V, which is right there, 35.5, divided by R, which I put right there, 0.0821 times T in Kelvin, 373. Okay, and then we can just solve those things. So I'm going to say 0.98 times 35.5, answer, divided by, and I'm going to use parentheses. Otherwise, my, please excuse my dear Aunt Sally, my order of operations is going to be wrong. 0.0821 times 373. Close that parentheses. Okay, I get 1.36, or 1.34 is what I'm going to round it to. 0.34. And again, what I'm looking for is N, moles. So the unit for moles is just mole, MOL. Okay. If we're going to move down here, and this time it says calculate the volume. So I can say this, pressure, I'm going to circle volume. Okay, they give me moles, which is N, and then they say at STP. Alright, so it doesn't look like they give me a whole lot of information. I'm solving for volume. They tell me moles, and they kind of secretly tell me temperature and pressure as well. Because I should know, or the periodic table knows, that standard temperature and pressure is 1 atm. Okay, so that means 1 atm is my pressure. And standard temperature, 0 degrees or 273, because I calculate in Kelvin. Say 273 Kelvin. So a lot of times people say, there's not enough information, I don't know. You do. They told you standard temperature, pressure. Alrighty, so now we can start looking at our equation. Pressure times volume, which is what I'm looking for, equals NERT. N times R times T. Now remember, R equals 0.0821. That's the ideal gas constant. Okay. So if I want to solve for volume, then I need to get pressure alone. Right, or excuse me, I need to get volume alone. So right now it's volume times pressure. So if I multiply and divide by pressure, then I have volume alone. So volume equals nRT divided by P. You can plug in numbers and move them around, but it's a little bit messier. I like doing it before. Alright, so then I can say my volume equals N, which is moles. I'm going to go 1.25 times R, 0.0821 times my standard temperature of 273, divided by my pressure, which is just 1 anyways. That works out nicely. Okay, so we can add that in our calculator, multiply 1.25 times 0.0821 times 273 equals, technically, divided by 1, which doesn't change it. So that's going to be 28.0, which I'm just going to go ahead and put 28. Alright, and volume. The unit for volume, if I look in my ideal gas constant, the unit that they use for volume is L for liters. So we'll go liters. Okay. Let's do one more. Let's look at that last one. In this case, they're asking me how many moles. So I'm looking for N of N2O, which should be a subscript, are contained in liters as a volume. They give me ATM, which I'm going to rewrite up here. And that is my pressure. And temperature, but I'm going to cross that out because I cannot calculate in Celsius. We calculate in Kelvin. So my temperature is going to be 25 plus 273. Okay, 298 Kelvin. Oops, I wrote the 8 first. 298 Kelvin. And then R is always right there. Our ideal gas constant is 0.0821. Alright, so again, I end up with my equation, PV equals nRT, and N is what I'm looking for. So to get rid of N times RT, I divide it by RT. That makes it cancel out. But if I did it to the right side of the equation, I have to do it to the left side of the equation. So we end up with PV over RT equals N. And then I can plug those numbers in. My pressure, 1.09 times my volume, 20.0, over R, 0.0821 times 298. And we just calculate it. 1.09 times 20 divided by, I'm going to use parentheses again, 0.0821 times 298. We'll close the parentheses. It was 0.89. And again, remember, we're solving for moles. So 0.89 moles is going to be my unit. Okay. I can't force it, but I very strongly recommend that you manipulate your equation, which really, this is the algebra, y'all. Do your algebra before you plug numbers in and make it messy. All right, let's look at the next page. The next page is a little bit more conceptual instead of calculating. I know some of you are better at that algebra than others are. So if you need help with it, come on in. These ones are on the back of your periodic table, and you should be able to do these things as well. All right, pressure conversions. This is a review from day 1 homework. Let's look at number 6. A pressure of, I'm going to box that in, and they're asking me for kPa. So pressure conversions, anytime I know like 1 foot equals 12 inches, or in this case, we can say 1 atmosphere equals 101.3 kPa. I can do dimensional analysis with it. So I'm going to put 2.10 atmospheres. That means I just go down my atmosphere unit, and I put what I'm looking for on top, which is kilopascals, kPa. And the top has to equal the bottom. So 101.3 kPa equals 1 atm, which means I'm multiplying and then dividing by 1. 2.10 times 1.3 by 1. Okay. 212.73. 212.7. And again, that unit is going to be kPa. All right. The average kinetic energy of a particle is measured by the temperature unit, Kelvin. Okay, remember we said Kelvin is a way to measure how fast a particle is moving, and movement is temperature. So that 0 Kelvin is absolute, looks like I wrote okay, but 0 Kelvin is absolute 0. That's the coldest it's possible to be, because it's not moving at all. So there's no such thing as negative 10 Kelvin or negative 40 Kelvin. That doesn't exist. All right, looking at number 9, if you leave a balloon in a car on a hot day, what happens to its pressure? Okay, so what they're saying is it's hot. So if temperature is going up, pressure would be going up. So if temperature is increasing, pressure is increasing. Okay, and why? That would be Gay-Lussac's law. Okay, it's a direct relationship. Okay, there's also a direct relationship between pressure and, volume and temperature. In a sealed, rigid gas tank, what happens to the average speed of gas molecules when you cool it down? So what this means right here, in a sealed, rigid gas tank, that means at a constant volume. Okay, it means it's like one of those big, hard helium tanks. So it can't get bigger, it can't get smaller. And the fact that it's sealed means that it's also constant moles. So if temperature is going down, what happens to its Kelvin? It slows down. Okay, when you cool molecules down, they slow down. Okay, what happens to volume in a sealed, rigid gas tank? We'd say it's constant. Nothing happens to it. What happens to pressure? Okay, so if I know temperature is going down, that's what we said right here, a direct relationship between temperature and pressure. That means pressure would be decreasing. Which law is that? Again, temperature, pressure, we just set up here is Gay-Lussac. Okay, the variables would be temp and pressure. Alright, and then we're also going to be looking at direct relationship. Alright, then looking at the last one, Boyle's law. Remember, that's pressure and volume. PV are hiding in Boyle's name. Okay, so if we're going to graph that, we'd say pressure on one axis and volume on the other. Okay, as volume gets bigger, so as I move out this way, pressure gets smaller. I start to move down. So that would be pressure and volume, and it's an inverse relationship. All right. Thanks, guys.